All right, I have the top of the hour. Good morning, everybody. I want to welcome you to the NCAT from Research to Implementation webinar series. We've got a great topic today. It's a little out of the norm for us, and I'm super excited about learning the information from our presenters today. But we're going to talk about IRI, or the International Roughness Index, and the texture data that can be collected on our asphalt pavements, typically with a high-speed van or at least a traffic speed van. So we're really excited about that. With us today, obviously, Nathan Morris here. He's our assistant director for test track research here at NCAT. He's responsible for overseeing everything on the track. He started his work in the laboratory, so he's got a really good rounded experience there, and he specializes in friction as well. And he has got three very busy children that he loves chasing around. It's a lot of fun. We also have with us today Grant Julian. He began his career at NCAT in the main lab in 2008 as an assistant research engineer there. His work focused on sustainability, and the use of warm mix, the use of higher wrap mixes, and even some shingles. Since 2008, Grant moved out to the test track facility there, and he manages the pavement distress data collection, which is not just limited to the track, but also goes out to our preservation projects. And he also does some nationwide awards for Napa and so forth. He also manages NCAT's inertial profiler certification program, which certifies about 70 profiling bands or profiling setups a year, and over 100 operators. This is both for DOTs and for vendors. So he stays very, very busy. We also have with us today Everett Schmidt from Pathway Services Incorporated. Everett has worked with Pathways for more than 20 years. During this time there, he's played an integral role as a research and R&D senior project manager. He's fostering relationships with clients both domestically and internationally. His areas of expertise are in new product development and design, specializing in road profilers, laser-based imaging systems, machine vision imaging systems, LiDAR, equipment design, and new technology integration. And there's a lot of new technology that's coming out in the pavement data collection. So we're excited to hear about all of that. I want to give a special shout out to JC3, who's on here, a great guy that does a lot of friction testing, and I'm excited to see him as part of this today. I want to remind everybody that we'd like you to stay muted during the presentations. Please put any chat or any questions that you have in our chat box, and I'll pop a reminder up in there. And all the questions will be addressed after the presentations are over. Given that, Nathan.
Great. Thank you, Travis. Can you hear me well?
Yes, sir.
All right. Yeah, I'll just reiterate what Travis said. Um, the best part of these webinars is getting feedback and answering questions from the group. Typically I learn a lot just to hear the back and forth between the presenters. So as you think of questions, go ahead and get them in the chat. Sometimes they spark discussion, as some of the presenters are answering in the chat in the middle of the webinar. And there's always great discussion at the end. It's really the highlight of the hour that we have. So that being said, I will introduce our topic today. Those of you who, Travis, are my slides advancing, thumbs up. Look good? Okay. Yeah, so those of you who might be new to the format, I'm going to give a very brief two-slide introduction, very, very brief, just to kind of prime the pump of what we're going to be talking about today. But then we have two folks who are much smarter than I am regarding our topic about really high-speed data collection systems. We'll be talking a lot today about smoothness and IRI and texture, but also looking a little bit forward to the future. And then we'll close out at the end and have some Q&A. High-speed data collection is something that it's not new. This is something that's been around for quite a while. I actually I'll show you in a minute. I was looking back through some of the original test track reports that were written, and we were collecting data and measuring texture with systems that were state of the art at the time. But since today we're going to be talking a lot about texture and a lot about smoothness, I figured I'd show, this is data that this plot that I'm showing you. This is, MPD versus the primary control sieve index, which essentially, is are you above or below the max density line? Are you fine or coarse graded? The data that I'm showing you here, these are from the 2000, 2003, and 2006 test track. Some of the fundamentals of macro texture measurement systems, are still still at play here. I use, even though uh, macro texture measurement has far exceeded where it was 25 years ago, and even 20 and 15 years ago, a lot of those fundamentals still apply. So I like to look at. I'm oddly fascinated with surface texture of all things, but especially asphalt pavements. Um, so Grant and Everett will have a chance to talk more about you know how these devices actually measure macro texture and how that data is being used in a network level pavement management system. Um, I'd say one of the biggest lessons learned for me personally, as it relates to data collection, is really the importance of how to use IRI data. The track is we're different in how we use these data. I like to say, we're a 1.7 mile oval track, but I have 46 sections with at least 46 joints. So IRI numbers on the track, you could ask Grant. I mean, it's not uncommon to see really smooth sections have IRI values in the hundreds. On the open road would be unacceptable. That's definitely not good. Um, but ever since the beginning, the data I'm showing you on the left, this is from November of 2000 and December of 2000. Um, this is the IRI of the test sections pre and post grinding of the transitions, which I've got a photo here from 2024, so many years later, of the grinding setups on those joints. You can imagine if you've got a joint and then 200-foot section and then another joint and then 200-foot section, you just have a lot of bumpiness. And we try not to let the bumpiness from the joints penalize the data that from the test sections. And so what I tell people all the time is don't worry so much about the magnitude of the IRI numbers, at least on the test track. Now, this is very, very different in the when you're looking at analyzing over miles or even tenths of a mile. Um, the actual magnitude of IRI is a lot more important. But what we like to look at is change in IRI over time. And that lets you know that nothing's happening. So even if your numbers may be elevated in the 80s, 90s, even over 100, if it's staying there, then that means nothing's happening on the track. And that's how we use IRI. It's one little example of how we use IRI and smoothness on the test track.
I'm going to talk about IRI and texture data collection at the test track. And so we'll first get into a little bit of background on collecting longitudinal profiler data and IRI. Then I'll talk a little bit about our experiences, the unique experiences with looking at this data on the test track. I'll talk about our profiler certification, and then get into just a little bit of where we are in the future.
John Helberg, audio trouble.
What we call, can you hear me?
Yep, keep going.
So get into where we're going in the future with the variable velocity profilers. So no discussion of profiling would be complete without mentioning the little book of profiling. We just released the second edition last year. Dr. Karameus and Dr. Sayers are the authors of this. The original came out in the early 90s, and they updated it last year to address some of the changes in the practice in the last 20 years. But I will use some figures from that book in here. But they do a really good job. Most of the principles in profiling are kind of mechanical engineering and electrical engineering related. And so for us civil engineers, I feel like this book does a great job of explaining it and giving us the tools we need to analyze this data. So what is a profile? Well, there's different profiles. You can measure longitudinal profiles, lateral profiles, depending on the data you want to look at. So a lateral profile would be information about rutting, distresses, cross slope. For the purposes of this presentation, we're going to be looking at longitudinal profiles. As we go down the road, basically, how does it relate to overall grade, roughness, or the absence of roughness, smoothness, and texture? So we just basically are taking elevation information as we go down the roadway. Mainly, we're going to be interested in what's in the wheel pass because that's what's going to affect our ride quality. So an inertial profiler, for any type of profile, you need three main ingredients to get a good profile. You need, and I like to equate this to surveying with a rod and level, because most of us are familiar with that. But you need a reference elevation, which in surveying would be your total station. For inertial profilers, we use the accelerometers to get that. And then we need a height relative to that reference. That would be your height of your rod. And here we will have a laser coupled with the accelerometer to give you your height relative to your reference. And then you need a way to tie it all together longitudinally. We measure it with a distance measuring instrument, whether it be a wheel encoder or GPS. But that's the three main ingredients. And so we're going to make sure that all of these are operating accurately when we start talking about testing with these. So just a few examples of profilers out on the market. I like to kind of group them in when we're talking about high-speed profilers. You've got your project level profilers and your network level. They all measure the same thing. It's just what they are set up to do. Now, that's not to say that a project level profiler couldn't operate on a network and vice versa. But in the project level category, you see aims, which is shown here, usually on a bumper mount. Simple, easy to use, gives you good repeatable data. The other main kind of player in that game is SSI. They have some different configurations. This is a higher mount. They also do some mid mounts where it's midway through the truck. And then the other group would be your network level guys, like Everett and Pathway, or Arb and Fugro, different players like that. They are more set up to run entire state networks, where they are going to measure not only smoothness, longitudinal profile, and IRI, but also take distress images to measure rutting and cracking, and take right-of-way images for signage and inventory management. So they're going to run the whole network one time and want to collect as much data as possible. But again, they will measure the IRI part, the longitudinal profile, the same way. So we measure a longitudinal profile, and we can glean a lot of information from a longitudinal profile. One of the main ones we want to do is we want to look at is a roughness statistic called the IRI, or the International Roughness Index. And the IRI was developed in the 80s. Well, it goes way back, but we won't get into the history. But it was developed and made so that it is sensitive to wavelengths that we will feel as a user of the system at highway speeds. So it's most sensitive to wavelengths between 3 and about 125 feet. Anything much longer than that doesn't play a part in what we feel for ride quality. And then much smaller than that would just be kind of noise in the data. And so that's a little bit of background about longitudinal profiling. I'm going to talk a little bit about how we use that at the test track and for our research purposes first, and some of the challenges we see. So like Nathan said, we have been using inertial profilers for 25 years here at the track. And here's some pictures of some of the older models. We started out with an ARAN on the front of this old Chevy van. We then, once it reaches the end of its service life, or the end of what the manufacturer will support, we will try to get another one and upgrade. And so then we moved to a Dynatest. And then from after the Dynatest bar, we have been lucky enough to have 3 models of the Pathway Services vehicles. So the bottom right corner is our latest model that we have. So we collect a ton of data with these things, with longitudinal profiles, transverse profiles, imaging, and sort that kind of stuff. But we're going to focus on the longitudinal profile data for this this talk. So again, when we collect a longitudinal profile, we are collecting elevation information to try to get that true elevation profile. From that, we can pull out a roughness statistic, what's going to make a car ride rougher or smoother. And we can also pull out information about texture and mean profile depth. The basics are you're going to be looking at a much smaller scale in order to calculate the mean profile depth, on the order of like 0.5 to 50 millimeters, whereas for the IRI, we're looking at 10 inches to 300 feet. But it can all be pulled now from that same type of equipment. Down here on the bottom, you will see our current setup. You see 3 lasers, and we actually will measure the MPD with that inside laser on the right. It's the same hardware as used for the IRI. It's just calculating different things. And so then on the outside, you will see the IRI lasers that measure the ride quality in those wheel paths. And you can see these are line lasers. They're about 4 inches wide. And so they do a good job of collecting a wide footprint of your longitudinal profile. Whereas 10, 15 years ago, we were using a lot of point lasers that collected a much smaller footprint and would give you issues with coarser texture pavements, which we'll talk about in a little bit. So some of the challenges we run into on testing on the track is, like Nathan said, those transverse construction joints. And we try to cut out some of the effect of that by cutting out 25 feet on either side of our typical 200-foot section. We call those our transitions, from paving startup to just having that joint. We don't want to negatively affect the ride quality, so we cut those out. But it can, if it's a really rough joint or you have a very rough adjacent section that's making you bump a lot, it can still be felt into the research section or into the next section. So that is a challenge to kind of isolate those effects of the joints in the rough adjacent sections. But like Nathan said, we like to look at the trend over time and not necessarily the magnitude of the IRI. And so those short analysis windows, when we're only looking at 150 feet, it means that having the accuracy of our DMI is vital, because if we're off a foot or two either way, it's going to shift the analysis section into where we don't want to look, and so it can skew the data. And so this is an example of just a snapshot of the IRI on our north tangent. It's half of the north tangent, so we can kind of see a little better. But you can see basically the spikes in IRI are going to correlate most of the time with a construction joint. And so the challenge is to get that out and not have it affect our ride quality as little as possible. But just the nature of IRI, it's going to affect it somewhat. And then this is kind of what we're looking at. This is just a sample of 3 sections over time, over the course of about a year. So these 3 sections are all right together, and you can see their IRI was pretty consistent over the first 5 or 6 months of the life, and then they all experienced a sharp increase in IRI. And the reason for that was we started seeing some cracking and some faulting. But cracking is small, low severity cracking is not necessarily going to translate to a high IRI. If you just have a small crack and there's no elevation change over the width of the crack, you may not see immediately the effect on IRI because your tire is just going to bridge over that. You're not going to feel it. But eventually, cracking is usually a sign that you're going to be having some deterioration. So we started cracking on these sections right around in here, and then it takes a few weeks, and then you start seeing some faulting in those cracks, and then you really start feeling it in the ride quality. And then down on the bottom is the texture on those same 3 sections, and you can see a slight positive slope on the texture, but for the most part, texture is remaining pretty consistent on these, even throughout that cracking. So yeah, now I'm going to talk a little bit about our profiler certification program here at NCAT. So we do all of our asphalt research in the right lane, and then in the left lane was historically just a construction platform or workaround if we needed it. But in 2009, ALDOT came to us and asked us to set up a certification program in order to certify project level guys in this that'll be operating in the state for QC purposes. And so we started establishing the site, or Jason Nelson did. Jason and Buzz started establishing the site, and by 2012, we're certifying about 10 or 15 profilers a year. And so we've really seen a lot of growth in that. And this shows kind of where we've gone over the last 10 years, going from about 10 a year to about 70 a year. We added Mississippi DOT. They now send their contractors here to certify. It's just I'll show you this. It's really good for the user because you have to make 10 runs on a particular pavement to certify. And with the track, you are closed to traffic. You just go around in circles. You don't have to stop and turn around. And so we're really blessed to have this facility here in Alabama to certify not only our project level guys, but if you go back to the chart here, you can see the gray are the vendors. So we've seen a marked increase in vendor participation in our certification because we do follow AASHTO, the AASHTO R56. And so a lot of states will recognize that certification and allow them to certify here and then for use in their particular state. So the certification sections, we have 4 sections and they are laid out according to R56. So you want a range of roughnesses to kind of put that profiler through its paces to make sure it can see all resolutions of roughness. The OGFC is a little different beast because it's not specified by AASHTO, and we are not going to compare it profile to profile. The reason for that is because, like I said, coarser texture pavements can, especially with the smaller footprint lasers, you can have a hard time getting repeatability on that because if you're on just a slightly different trace, your laser is going to fall off in a hole or maybe on top of a rock. And so it's harder to get repeatability and accuracy on the OGFC historically. Now with the wider footprint line lasers, it is a lot better. But is still what we do is we just look at an IRI to IRI comparison on our OGFC. And so it's not really as stringent as the dense graded, where you're looking at profile to profile comparison. So some of the requirements in that R56, you want to check your lasers with the block test, you check your accelerometers with the bounce test, and then you check your DMI with rolling a known distance and seeing if you're within 0.15% of that true distance. And then you really get into the meat of the certification by making 10 repeat runs on each section. And currently what you have to make or what you have to meet on that is 92% repeatability, which is comparing to yourself, and then 90% accuracy, which is comparing to a baseline. We use a Serpro rolling inclinometer type baseline currently. And so you roll that Serpro at walking speed, you're on that trace, you do it at least 3 times and make sure you get 98% cross correlation or repeatability. And that is your ground truth, your baseline. And then so the units have to meet that within 90% accuracy. On repeatability, remember that's a little higher at 92%. And this is about 300 attempts over the course of several years. You can see that most people don't have problem meeting repeatability. Most people are north of 96% repeatability. And the accuracy is generally what most people are going to have problems with, is meeting that accuracy. And the simple reason for that, 99 times out of 10, it's going to be because they are not following the same trace every time that the ground truth is on. So they're have an offset on that. And so again, that's what most people have problems with is the accuracy. So you can see there's much only, especially on the smooth section, which is in the blue. Um, the smooth section has a lot less room for error, and only about 25% of our units that we see here get above 94%. There has been, some push to up that 90 and 92% to 90, say 94 and 94, to make sure we're getting, even better numbers. The way it looks right now, I think we could do that with repeatability. We may need to, on accuracy, look at maybe more like 92%, based on our numbers. But for right now, like I said, it's at 90% accuracy, 92% repeatability. And so the last I'll end with is talking a little bit about the limitations of our typical high-speed profilers. Because they use vertical accelerometers, which like to be kept vertical. If they are not vertical, if the accelerometer does not stay vertical, it will badly skew your results. So that is in places where you have to brake hard, accelerate, decelerate. You picture the accelerometer, when you accelerate, it's going to kick back and not be vertical. And so you're getting some erroneous readings. And also in dynamic traffic patterns where you have sharp turns or roundabouts where it'll be thrown off skew. So that is historically some of the limitations. We just don't look at IRI or smoothness in those areas where there's braking, and so that is a challenge in urban environments, where you have a lot of stops and goes. And so the industry has done a great job of addressing that need in the last 4 or 5 years, in what we'll call variable velocity profilers, where they are able to calculate IRI and measure good profiles in dynamic stop and go situations. And this is just maybe not a comprehensive list, but all the vendors have their neat little names for them. I think Everett told me variable velocity profilers is a good generic term to use. But yeah, so they've all got their names, but the basics of it is they're adding a laser to each side, so that they can help the accelerometer account for that, when it gets off center, when it gets off its vertical axis. And so for that, AASHTO R56 was actually updated just last year to account for these variable velocity profilers hitting the market. And it is going to be much more time intensive because it requires more runs, more stop and go, which is going to make, for longer days. But it is, I think, a necessary evil, especially if your unit is going to be operating in urban environments. It makes it easier. Like say you're collecting a big city. In the past, you may have had to hit that at 2 o'clock in the morning so that you're not seeing a lot of traffic. But with these variable velocity units, you can pretty much collect any time of day. So yeah, I won't get into, but there's 4 different scenarios where you want to basically put those variable velocity units through their paces, and they have to meet the same constraints that we do at our constant speed runs. And I think I made the time limit, and I guess we'll save all questions for the end, and I will turn it over to Everett.
So there'll be a little bit of overlap here, with what Grant just talked about. But just to recap, my name is Everett Schmitz. For those of you who don't know me, I'm with Pathway Services. We have a litany of other technologies, but Nathan asked me to talk a little bit about particularly texture and how that relates to the high-speed data collection systems. So just a little background on our equipment. This is the piece of equipment that my company manufactures. It's called a Path Runner. We have a kind of a litany of data types that we collect. I'm not going to get into all the details, but These are some of the systems that we have. The primary ones that we're going to be talking about today are generated from the bumper of the equipment. So we've got our ride quality IRI and our macro texture systems. So just to kind of recap what Grant was talking about, and for those of you who may not know how the systems entirely work, I hope this isn't too elementary for everyone in the group, but just to kind of recap. So when we're collecting a longitudinal profile, you've got a laser coupled with an accelerometer. There's a lot of engineering science that goes in behind that, but the kind of the gist of the point is that we're using a height measurement on a laser and sampling at some interval and generating all these elevation points and then stacking those in the longitudinal fashion so that you are measuring kind of what the wheel paths would experience in a road. So historically, that was done with a point laser. I know that's been quite some time now since we've kind of moved on to the line lasers, but I kind of want to highlight why we're changing to that and some of the things that we encounter. So this is a top view from the pavement, and if you've got a single point laser, you'd measure that longitudinal profile, and you'd come up with these points. So this is looking at the side. So you've got your points in the longitudinal direction that the vehicle drove. So as Grant mentioned, the repeatability is the hardest part. So he says, go back out and run it again. And I move over even a half an inch can affect this. So when you're trying to get repeatability, you can see just how different these points are. Just moving very, very slight differences. It doesn't matter if you're the best driver in the world. Moving very small amounts when you get into the texture particularly can affect that. And then the other problem is you have vehicle wander while you're traveling. So you get this third profile, and not only is the shape different, but you are also battling a distance problem where the length of your profile may vary as well. That's not quite as significant, but it does play a role. So the fact is that the vehicle path it greatly affects the repeatability when you're trying to measure the longitudinal profile, and especially when you're encountering this with the single point. This becomes a pretty significant problem when you have very highly textured surfaces, such as these here, or if you have any sort of grooving, grinding features that exist on that pavement. One example I've got here, and it might be kind of hard to see, but this is a section at NCAT that has some longitudinal grooving that's been applied. And you may not be able to see that on your screen, but I kind of highlighted. These are all the pits that you're going to be trying to battle when that vehicle's moving back and forth. This is what that type of pavement kind of looks like while you're zoomed in. And the problem is when you're driving along, this little dot hops in and out of those grooves. Okay. So the problem is, and we'll kind of recap the longitudinal profile here. As you collect that data, you get these gaps where the laser dropped down into the bottom of that groove, and this can create an artificial height measurement. So I'm trying to average, the height of all those points to see where a tire was riding across the road surface, and I'm getting this artificial height difference. And depending on the texture or the grooving depth, that can affect your height measurement 20%. And so as Grant mentioned, when you're trying to get repeatability better than 92%, you will 100% fail if you try to do this. So what we found, and historically this has changed, is that the point lasers do not accurately represent the tires because of the difference, unless you're driving Grant's car that has real skinny tires. I kind of had to throw that out there. So what has the industry done to solve this? About 15 years ago, there were a lot of laser systems out there that started generating a line or a footprint laser. They are historically around 100 millimeters wide. There's some that are narrower, some that are wider. But the idea is that you are now trying to represent what the tire is actually experiencing. There are certain features on some pavement types that we won't mention on this meeting, but they don't play well with having the orientation of that laser in the transverse position. So most systems are going to be oriented around 45 degrees. There's some that are 10 degrees, some that are 60 degrees, 70 degrees, but generally speaking, you want that to be rotated about 45 degrees so that the grooving or other featured texturing is kind of accounted for in both directions. So what that looks like now is you have a line laser that is now getting kind of a swath that it is able to capture. The science behind that is this will be kind of a very simple explanation, but now this is in the transverse position. So this is if you were standing behind the vehicle looking forward, and you get this line on the ground. It is a line laser, but what the camera turns that into on the device is a whole bunch of dots. And those points then are now kind of arranged in that transverse direction so that I kind of know, or if it's turned 45 degrees, it's a cross section of that pavement surface. And where that helps us is historically we had this little dot, right in the middle of the tire. And as you can see, in many cases where that's not accurate. So now we have a line that is, simulating where the tire is going to fall on top of that aggregate. So we have a new feature we call the bridge value. And this is what Grant was talking about, where you're kind of smoothing out that surface. But what this does is it looks at all of these peaks and valleys, and it kind of assesses and says, this is where a tire is going to be resting on that pavement surface. And so we get what's called a bridge value or a bridge height. And that is more or less the average depth where a tire would ride across the surface of the pavement. Now this can be done in real time, and you just the laser will spit out just a single height value. Generally it's done 3,000 times or more per second. So it is a very, very fast observation. Or you can store the raw data and you can come in and adjust some of those parameters. There's been a lot of research done lately to simulate just exactly where that tire interaction occurs. Obviously, the tire doesn't ride across all the peaks and it doesn't seek down into all the valleys. And it's not generally halfway between. It depends a lot on the durometer, the hardness of that tire. And that obviously varies from vehicle to vehicle if it's a small car or a heavy truck. And some of that stuff has to be accounted for. So once that bridge value is determined, then we can basically, for the time being, we can ignore everything that's below that contact area, and that data won't be discarded completely, but we'll basically fill in these gaps and throw out all the stuff below it, and then we kind of bridge those pieces between, which is where that bridge value comes from. And you can see where we basically connect the dots or interpolate. So where that comes into play is now we're back on this longitudinally grooved section here. And what used to be just a single path, again, the best driver in the world, you're going to drift. And when you're talking about grooves that are separated by 3/4 of an inch, you don't have much flexibility there. So now we have a path that is much more representative of what the tires experience. So that's kind of where we've evolved over the last 15 years, and it continues to improve. Resolution gets better, accuracy gets better, the bridging algorithms are always being improved. So we're trying to make constant improvements on that system, which has led, obviously at the end of the day, you get a better snapshot of what the conditions of your pavements are. But we started looking into this, and there's a lot of information that is still available from those lasers. We're using this one laser to essentially estimate where the tire is on that road surface for IRI. But there's been a recent, push or request for what other information can I get out of this? So if we go back to this bridge value, with the high resolution systems we've got now, we have we're much more apt to kind of do a fine assessment. We're no longer looking at just the kind of the big number, which is IRI. That's your long wavelength features. Now we can start looking at things like texture and voids. And where this is important is I saw a message pop up. Someone was asking about the friction. There's always going to be some moving targets when it comes to friction and texture, but one thing that we really want to start looking at is what do these surfaces look like where the tire is actually interacting, with that wearing course. And as you can see here, these can be wildly different. You can have a lot of texture on the top, and you don't, if you have a groove surface, there's no texture down on the bottom, but that's kind of rendered useless in terms of tire speak, because the tire is not actually ever going to contact that area. This is a sample of what a groove pavement could look like, where you have a lot of texture on the top or you have a lot of texture in the bottom. And identifying where that texture exists is a key element when assessing the pavement condition. The MPD for these two pavements would be very similar, but they would behave very differently when you introduce water, especially. And we'll bring this guy back in. This is a prime example of that. In addition to the texture, we also have the ability to look at these voids. So we're not just discarding that data. Those voids play an integral role in how the pavement performs as well. And so we want to see what sort of connectivity we have in the openness of that pavement, where we want to get that water out of the way, whether that's in the form of a groove or if it's in the pavement design, if it's no GFC, where we need to get rid of that water and still maintain some level of connection between the pavement and the tire. That kind of brings us into some of the newer things that we're investigating and dealing with, where in reality, not all roads need the same level of friction. If you have a long straightaway, obviously, if you need to slam on the brakes for a wild animal or traffic backup, whatever. But generally speaking, if you've got X number of dollars to spend on a system on your road network, you're going to have to evaluate where your needs are and where your wants are. We would like all roads to be identical and have the same wearing course and have the same condition, but the reality is that you have higher traffic counts, you have different weathering conditions, you have different material types, and those all play a role into how that pavement deteriorates and how you're going to be able to treat that. So in this case where you just have a long straightaway, I'm just going to keep going, and I'm really mostly concerned about my ride quality at that point. So if you don't have any need for stop, we want to maintain some level of potential friction from that pavement. We can analyze those profiles and kind of assess that, but some of the tools that we're working on, they'll help you identify where some of that increased friction is needed. And while the lasers will essentially, at least probably in my lifetime, they will never actually be able to tell you what the friction is, because you're going to have other environmental elements, such as raveling or artifacts on the road surface, whether it's in the form of leaves or petroleum byproducts that you're coming off of vehicles, that kind of stuff. The problem is the laser is only going to capture what it sees on that wearing course, and if it does not know if that wearing course is falling apart, if it's moving. But we can do some year-to-year comparisons and see how much that's occurring, if there's some polishing going on or some delamination going on, or that aggregate's starting to break apart. And by evaluating these different components, then we can kind of estimate what are some of the predicted safety performances on where that the friction is needed, and where do I need to get rid of my water. And this, as Grant mentioned, also you have other conditions, particularly radiuses, where maybe some of your cross slope isn't adequate enough, or you've got ponding or poor watershed. So as we get into these intersections and that kind of stuff, we want to know how much potential friction can I achieve, or how much water can I get rid of, because we can't always rely on the vehicle tires to do that. The vehicle tires from road users, it varies wildly, and so we want to have the pavement be able to achieve as much of that functionality as possible. So in short, with the continued development of the high resolution, high speed technology, we're getting more and more data types. We're getting more and more measurements that are available, and increasing agencies and users to make better decisions, to spend their money better, to plan long term, to integrate long term performance plans, to make our roads smoother is always the end goal, but this ultimately will fall down to safer roads, and that's I would hope is everybody's goal, is to have as safe as road as possible. So just want to throw this out there. Hope you guys find some humor in it. I think a lot of people would enjoy that. So any questions or comments will be available for.
First of all, thank you to Grant and Everett. That was excellent. So a couple recommendations that I took away from y'all's discussion. One of them, Grant, I appreciate you highlighting the new and updated resources for smoothness and IRI, specifically a little book of profiling and both of those being basically hot off the press. So a lot of new information in there, updated information, as technology is constantly developing in this area. And Grant, I liked how you touched on there are improved methods that are coming out to address the deficiencies of existing profiling systems on really any sections that would affect your accelerometers. So, slow moving traffic, stop go traffic, accel, decel lanes, sharp turns, things like that. And so, be on the lookout for, especially for any network level, agency folks on here. This is something that is going to, I think, improve the amount of information that we're getting from our pavement network, especially in areas that maybe traditionally we were unable to capture or to collect either in a reasonable time frame or maybe even at all, due to speed differences and things like that. Everett, you talked a lot about the deficiencies of point lasers versus line lasers. I think I love that. I've got a core. You may have actually stolen mine to take that picture. The core of the grooving is just such a wonderful picture. If to help understand what texture is and how to measure it. And I thought your animations, describing the deficiencies of point lasers was really helpful, and really giving more background of why the industry has moved to line lasers.
I would say on that note, Nathan, while the industry, I think as a whole, has moved to line lasers, there are still a lot of systems out there that use point lasers. And I think users and agencies need to be aware. I'm sure there's people outside of just kind of the larger state networks that would be interested in this, particularly some of the municipalities and counties and MPOs. But it's making sure that you know what technology is being used to capture your data, because I'm still shocked to see how many systems out there are still relying on point lasers. So I just wanted to throw that out there, that
appreciate that, and that's I think that's one of the reasons I wanted to highlight it, at least for the 140 something folks who are on this call, on this webinar, is the technology still exists out there, but you got to recognize kind of what it is that what are the capabilities of your equipment, and what are the data actually telling you? How might you be being led astray by? Because the numbers may be the same, but if the systems collecting those data are different, and one of them is a vast improvement over another, that's something that agencies need to be aware of, or any users, not even just state DOTs, municipality levels and things like that. And then I appreciate it, as somebody who spends a lot of time thinking about the interface between vehicle tires and pavements. I appreciated, Everett, your comments about how texture measurements of the area that's actually in contact with the tire is really of the most importance as it relates to safety. And those of us who are familiar with macro texture measurement systems and different macro texture parameters, we know that not all you can have two surfaces with the same MPD, but have very different surface profiles and very different effects on safety and vehicle ultimately crash data. So I appreciated your commenting on that. And then finally, I think it's a pretty honest assessment of the state of the industry. You go to TRB and maybe there's a poster or two about how laser systems can measure friction, but in general, we're just not there yet. It's really hard to measure friction when that is a response of a tire between, on top of pavement. Lasers just can't do. And Everett, I thought your examples about how, you scan over, a fuel spill or, debris on the pavement, and, the laser doesn't know. It's just going to tell you what it's looking at. So we're not quite there yet, but I do think, and there's a couple of questions we're going to get to. I think we're getting closer, and I think that the information that we're getting is better than what we've had in the past. So that ultimately, with the main point being, for safety, I think our data are we're a lot closer than we have been in the past. So with that, we'll just go ahead and go over some questions. And there's our emails for those of you who are interested. And what I'm going to do, Grant and Everett, I'll look through some of these questions. And some of you guys have already gone through. But a question from Dave, and Grant's already answered this, but Everett, I'm not sure if you have any comments. Are there any recommended minimum horizontal and vertical curve thresholds where ride quality measurements are considered unreliable? Everett, do you have any comments on that?
I do know that there's been some, there is testing being done to see. I think the first stab at refining the R56 certification was simply how do we account for the the influence of those vertical accelerometers that were historically used, and how do we get away from those by using any number of methods to account for the vehicle pitch. And I think roll is the next field. I don't see that very far off. We've done some initial testing and had pretty good results, but it's really, really hard to get a reference profile to compare that to in those curves. So you kind of, I think right now we're kind of at that 80% trust threshold that most of the systems out there that are measuring the variable velocity, the fashion that data is being collected, it's not going to be as susceptible to the lateral movement, and should handle that quite well. But there is no, to my knowledge, there is no standard that says, you can't measure anything over a 3% grade or a 1,200-foot radius or whatever that might be. I know that, again, the data that we've looked at, it looks pretty good, but we don't really have any way of stamping that and saying, yep, this is certified.
Great, thanks. Another question, really for either of you, just digitally arm wrestle over it. Is would it make more sense to have less device-specific testing speeds for contractor variable speed devices to encourage more contractors to move toward those newer devices with advanced capabilities? Or are the testing hurdles for variable speed profilers only applicable to the manufacturers certifying new devices?
No, I don't think they're only applicable to new equipment. It really depends on the state you're in and the application you're going to be using it for. Like Frank said, in Alabama, we don't currently have ride quality as a pay factor on low speed, low volume roads. And so the investment in the newer technology, because there is an added investment, is not really necessary. Now, if you were working in New York City, I think it would be definitely needed. I don't know if you have anything to add to that, Everett.
Not really. I mean, I think it's there will be some growing pains over the few years, the foreseeable future of getting everyone to adapt to those, but it's kind of the necessary evil when it comes to if you're wanting to capture accurate data, you've got to use the right equipment to do it. So um, I think it's kind of case by case, and like you said, Grant, if you get into places like New York City or larger cities, it doesn't have to be New York City, Seattle, Dallas, Chicago, Houston, Atlanta, all those places, and the contractors exist everywhere, so they're going to have to um, sort that out. But I don't think too much different than that.
So our friend Frank Bell from Aldot has also been active in the chat, answering a couple of questions and helping out. And so, Frank, thank you for sending that links to help people know what states are looking at, what systems they're currently specifying. So I encourage folks to check out the chat and click on that link. There's a discussion in there about how many different um, uh, uh, profiler certification testing sections are there out there. Um, another question I want to get to is from Hamid. Is there a full width lane laser scanning system that can be used for capturing the extent and severity of segregated area as a part of quality control or acceptance?
Yeah, the 3D measuring systems, the Pathway 3D Pass, can detect raveling.
Can it detect segregation in the mat like pretty quickly after uh, a new overlay has been constructed?
Everett?
I'll say yes-ish, and even I do want to put an asterisk on the raveling. Again, lasers can't measure things that are moving. We can the delamination is kind of a lower hanging fruit, but you have to kind of do some back-to-back comparisons to really nail down that raveling. But the 3D system will definitely identify that as a full lane. It's a 4 meter wide scan, and it's 1/8 inch longitudinal resolution. You get 1 millimeter distresses, so you'll definitely see that.
Another question from Eric Ranks. Says comparing year to year roughness makes sense, but will we run into a continuous problem of the technology constantly improving and changing the baseline? I think that's a big question on anybody who works in a testing environment. Is as tools change, sometimes your baselines change. So how is the industry trying to address that issue?
Yeah, that is an issue, not just with roughness, but with distress measurement. As the 3D systems are able to see more, they may classify more cracking than they did before they could see it. So it looks like the network is getting worse when it's just actually measuring more. Yeah, it's Everett in Pathway work with a lot of states. I don't know, each state is kind of different. I don't know how exactly they handle that.
I mean, a lot of it just comes into education on the systems and identifying that, like you said, just because improved resolution or improved data doesn't mean you're going to improve your road network. You might actually be identifying problems that you were missing out on before. And that's, again, kind of one of those necessary evils. It's a byproduct of improved technology. And just because you didn't see it before doesn't mean it didn't exist. But I think if you made educated decisions, based on the information that how much better is your resolution, how much better, with the all speed data that we're able to collect now. Previously, especially in urban environments, you were probably missing out on. I mean, it could be 25 to 50% of your network because you were driving too slow, you were accelerating, you were braking, you were turning. And so now you're going to be able to report, data for all those pieces. And my guess is your numbers are not going to get better. Intersections historically have worse ride quality numbers because of shoving and heaving and other problems that are inherent to intersections. That doesn't mean that those didn't exist before. It just means that you're going to start seeing them now. And so I think you will run into those issues, but it's a necessary evil. It's kind of like saying I didn't have a cavity until I went to the dentist. Um, you know, if somebody sees that, then it's probably there. It's just that you may not have seen it before. So it is a challenge, but I think it is necessary.
I think that's a helpful answer. Are there any data on how road debris affect IRI, or is that sort of outside of?
100%. If we get into situations where there's, especially in the fall, um, I think I saw some folks from Massachusetts on the meeting, and you get into situations where the west part of the state, we have to collect that before the leaves start falling, because the moment the leaves start getting on the road, I mean, the lasers, again, they will only take a picture of what they see. And if you have, something covering your asphalt, it will 100% affect the ride quality numbers that you're getting, and not in the positive direction.
And so what can you do other than physically removing the debris to filter those data?
That's the only option. I mean, you can't make up data. You can't assume how much the leaves are affecting it, or any other sort of debris for that matter. We see instances where, and these are far and few between, but especially like in front of construction sites where you get a lot of mud buildup coming out of a construction site on a road, and some of that stuff can drag on for thousands of feet if you've got lots of traffic there. And you look at the data and say, man, this section of road got 40% worse over the last 6 months. What happened? And then you go look at it, you say, oh, well, there's a bunch of mud on the road, and you can't crop that out. The lasers are only, they're just the messenger. And so how you deal with that, you pretty much have to collect it when you don't have any debris on the road.
That's a good point. I'm gonna step back. And by the way, we are over time, so I appreciate you guys hanging on for a few minutes. But this is a really good discussion and lots of engagement in the chat. I'm gonna go back to the previous discussion about improving technology, constantly changing a baseline. And so Frank Bell made a pretty good comment about improving technology and finding more distress or identifying more distresses. It can be particularly troublesome if you have some legislated minimum condition. And so if any codified minimum condition level is not also changing with the improved systems, then things will appear to be worse, even though in reality they are not. And so if there are mandated threshold numbers to hit, those thresholds need to also be changing along with the technology. So Frank, I thought that was a really helpful point. And then I'll go back to the question about the road debris. Blair Heptic sent me a direct message saying, is there a minimum scallop length in the IRI algorithm that would filter out like a piece of gravel or rock on the road to help remove maybe some of those individual points from skewing data?
I think there's some filtering you can apply. Depends on what your assessment or the analysis level is. For network level, for IRI, a piece of rock here and there is not going to affect it dramatically. I mean, if you're trying to do a certification, obviously you want to have as clean of a site as possible. But in the grand scheme of things, if you're talking large network collection, a little bit of rock here and there, that's going to get filtered out in your long wavelength filtering. If you're talking about the texture, again, it depends on how many pieces of interference or debris you have. If it's a piece here and there, it probably won't affect it that much. If you get into, larger segments, again, sorry to sound like a broken record, but the lasers only report what they see. And so if you can filter some of that stuff out, but if you start filtering out too much, then you're going to negatively influence that end result, which is not desirable.
Yep.
Hope that makes sense.
Yeah, so a couple more probably easy questions. So Amir asks, from a producer's perspective, is there an early warning signature in the high-speed profile data or texture data that can show the surface is heading toward cracking or faulting before that distress is actually visible? So in other words, like, is there a trend or is there something that you can see as an early warning sign to pick up a construction quality issue before it actually shows up?
I think you could rely on performance curves pretty heavily on something like that, but you will get into a situation where the short answer is you could guess with a high level of confidence in certain cases, but without having a crystal ball, obviously you're not going to know exactly where the problems are going to be. But there are certain distresses that tend to behave the same way, and so if you start to see this openness, you could work with there are companies out there that really just focus strictly on this kind of information, but you could say I've observed that this distress went from 1 millimeter to 2.5 millimeters to 2.5 millimeters to 3 millimeters, and that's a relatively small distress. It's not going to be affecting your ride quality, and so I think you could use those to identify a rate of failure that's occurring and say, okay, well, I've got 2 years before this is going to become a major problem, or I don't need to worry about this right now. But yeah, there's a lot of data out there that you could use to build these performance curves. That's not something that we particularly do, but I know there are companies out there that do things just like that, and year over year, and even short term analysis if you did month to month.
So we got time for one more. So Ed Norris asks a follow-up question to Frank's comment about legislated targets. So he asks, is there any consideration from the Federal Highway Administration to revisit ride quality targets due to the advancements in the all-speed profilers?
Yeah, Everett, correct me if I'm wrong, they were revised relatively recently in 2017. And yeah, Frank makes he thinks you are able to revise targets for the TAMP if your justification like a new technology. But the 2017 change actually made it more stringent, if I'm remembering correctly.
You mean for the thresholds?
Yeah.
They were set higher, and then they were brought back down at basically the voting committee did not agree on trying to implement too many changes at once. We have seen those thresholds get tighter and tighter every revision. I kind of have mixed feelings about that. I think the technology is lending itself to make that easier to do, so you don't want to kind of throw in the towel and just say, oh, I give up, we can't do any better. It does knock some of the contractors. They may not have the ability to clean up some of the data like what we do, so it's kind of a double-edged sword there, but I do think that number will be probably going up in the near future.
All right. Well, I want to just one more time thank Grant and Everett for your time. This has been a very, very informative, great webinar. Thank you to everyone who asked questions and even answered questions. I see, Jerry and Frank chimed in. A couple other folks chimed in in the chat to make it more engaging. This was really, really good. Travis said at the forefront of this is a little outside of kind of what we would maybe typically, talk about on, materials or pavement, but I thought it was a, 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 it was an excellent topic to bring to the forefront. So thank you again. Two excellent presentations from Grant and Everett. So if you want to know more about things related to the test track, you can visit us at our website at ncat.us, and there's all kinds of information there. You can go and read test track reports or find old data, and I thought it's a really helpful resource. Anybody looking for particular training? So normally Travis is pushing training in their pocket. This is something that's growing and growing and growing. It's really helpful resources online for maybe something a little more quick to understand different test types or volumetric chart, things like that. But if you're interested in larger, more formal training opportunities, Travis has a pretty robust training system where either you guys come to NCAT or NCAT will just kind of take training on the road at various locations. So things related to mixture and mix design, but also pavement design and management and all kinds of things. So with that, save the date, March 19th. So same time, third Thursday of the month at 10 a.m. Central Time, we will be talking about cracking tests correlated to field performance with Dr. Randy West. So the director of NCAT will be one of our featured presenters and to talk about all of the work that was done to take cracking tests and correlate them to field performance for use in quality assurance programs. So thank you, everybody. Thank you for your attention. And with that, we will conclude the webinar.